A researcher theorized that average heights of boys and girls of the same age prior to undergoing puberty should be the same. 58 randomly selected boys of age 8 had an average height of 123.5 centimeters with a variance of 98 centimeters. 55 randomly selected girls had an average height of 126.1 centimeters with a variance of 119 centimeters. Use a 1% significance level and the p-value method to test the claim that there is no difference between the average heights of boys and girls at age 8. So I can see clearly it's a hypothesis test. That's why I've underlined this phrase, to test the claim. And also apparently they want us to use the p-value method in the problem. Whenever you know it's a hypothesis test, the first thing you should do is to try to express the claim, right? Symbolically. So I see this phrase, to test the claim that there is no difference. What does no difference mean? It means they're the same, right? So we're going to test the claim that there's no difference between the average heights of girls and boys. And it says average height, so we're talking about the mean height. So let's say that the claim here for this problem then is that the mean for, and I'm going to put boys first here, the mean for boys is equal to the mean for girls. All right, so that's our claim, that the mean for boys is equal to the mean for girls. The next step is going to be to express the HO and HA, so our competing pair of hypotheses. So we'll get our HO and our HA next. All right, so when I look at the claim, I see that it has an equal sign. If the claim has an equal sign, it means it's the same as HO, because HO always has some sort of an equal sign, right? So we'll have the mean for boys is equal to the mean for girls in this problem. And then for HA, it'll be just the opposite of that. And of course, the opposite of equal to is going to be not equal to. Okay, so there's your first two steps, your claim, your HO, your HA. Your next step in the problem is to list all the data that we're going to need. And this problem is unique in that it gives us the variances instead of the standard deviations. So I want to pay attention to that because it's an easy mistake to make to use the variance as the standard deviation. So you gotta be careful of the language there. It says clearly it's the variance that's given. So let's copy down the data for the problem. We actually have two sets of data, right? And we actually have a little group of data for the boys, and then we have a little group of data for the girls. So we want to make sure that we keep those distinct, right? So for the boys, we're going to have a sample size, we're going to have a sample mean, and we're going to have, in this case, a variance. Now, they don't usually give you the variance, but they do in this problem. For the girls, we'll have the same thing. We'll have a sample size, we'll have a sample mean, and we will again have a variance because this problem gives us the variance. So because it's variance, I'm writing S squared. All right, let's look at the boys now. In the case of the boys, it says that 58 randomly selected boys of age 8 had an average height of 123. So there were 58 boys. The average height was 123.5 centimeters. In the case of the boys, the variance was 98 centimeters, so 98. Now for girls, there were 55 randomly selected girls, so the girls were 55. It says that they had an average height of 126.1 and a variance of 119 centimeters. All right, and the last thing they give us in the problem is they tell us the significance level, alpha, and they say that that is 1%, so 0.01. Okay, so we have our step 1, the claim, our step 2, hypothesis, step 3, we have the data. Let's go on to step 4, which is going to be to come up with our test stat. Okay, so for the test stat in the problem, we need to know what type of hypothesis test we're conducting. Well, I look at these samples and I say this is large samples and we're comparing two means. The samples here are independent. In other words, this group is boys. They're separate and distinct from this group of girls. So it's independent data. So we're going to say it's a large sample independent Z test. So that means we're going to have to do the test stat related to Z. And the formula for that is going to be pretty simple. We're going to basically subtract the values we have here for X bar, right? So we're going to say on top that it'll be X bar for boys minus X bar for girls. And then at the bottom, we're going to put this complicated square root for the problem. So this square root is going to basically be the variance. So normally it would be sigma squared for the first group, which in this case is the boys, divided by the n for the boys, plus the variance for the girls, divided by the n for the girls. And that's the formula for your test stat. Okay, so let's plug in those numbers then and come up with our test stat for the problem. So when I put the the sample means in for the boys, I get 123.5 minus the value for the girls, 126.1. All of that divided by the square root of. And we have the variance for the boys, that's going to be 98, right? Over the sample size for the boys, which is 58, plus the variance for the girls, which is 119, over its sample size, which is 55. And again, notice I don't have to square them because the variances are already squared, and we're using the sample variances as replacements for the population variances. Okay, let's use our calculator now and we'll work that out and see what we come out to get. So plugging that information in, I'm going to have up top 123.5 minus 126.1, close that up, divide by the square root of, and that square root is going to be 98 divided by 58 plus 119 divided by 55. And I'll close that up. And when I'm done, I get the answer negative 1.32. Negative 1.32. So our answer here is negative 1.32. That's our test stat. All right, now normally in most hypothesis testing problems that you face, they're going to ask you to come up with the critical value, but in this problem it says use the p-value method. So our next step is actually to do the p-value. When you're doing the p-value, you want to draw the bell curve. But you don't put tails on it. What you do instead is you just put the test stat where it belongs with respect to 0. So if that's negative, it's going to be on the left, negative 1.32. So I'll draw a line representing where that's located on the curve. And then what I do is I look at the type of test that I'm dealing with. If it's a two-tailed test, the rule for the p-value is you find the tail area beyond the test statistic, and you double it because it's two tails. So I'm going to have to look up this area, and then I'm going to double it afterwards. All right, so let's go to our table and look up 1.32 on our z-table and see what area we get for that value. Okay, so now we're looking up the value 1.32 on our z-table. Let's see, there is the 1.3 row, and then the third column over 1.32, we get the value 0.4066. 0.4066. Okay, so now we have our value from our table of 0.4066. Okay, so that's the value from here to the center, right? That's not the area in the tail, though. In order to get the tail area, I have to do 0.5 minus 0.4066. And after doing the subtraction, we'll get 0.0934. Okay, so about 9.34%. But that's not our p-value because remember in a two-tailed hypothesis test, and two-tailed based on the fact that it's not equal to, we have to double this value. We have to take twice of it, right? So we'll have 1868 after doubling it. So in other words, our p-value is equal to twice this value, which works out to be 0.1868. All right, so our p-value is quite large. Our next step in the problem is to compare our p-value to alpha and see which is bigger. So I think it's pretty clear that this p-value is greater than the alpha of 0.01. And since that's true, our initial conclusion is as follows. We're going to say that we do not reject HO, and therefore do not support HA. Remember that when our p-value is large, we do not reject HO, and as a result, we do not support HA. So that leads us to our final conclusion then. We have to look at our result here and see what that says about our claim. So our first thing we want to ask is, which is our claim? Is our claim HO or is it HA? Well, it looks like our claim is the same as HO. So I'm going to use this wording then because our claim is basically HO. So I want to use wording that says we do not reject HO, and therefore we do not reject the claim. So I'm going to say the sample data does not allow us to reject the claim. The sample data does not allow us to reject the claim. And of course, the claim here is that the boys and girls have the same height. So basically, we're saying that these two heights are the same at this age, and according to what we've done here in the hypothesis test, it seems like that might be true. So the bottom line is we're not able to reject that idea, and basically what we're saying is that because of the effects of puberty, boys eventually outgrow girls. They start to get taller and stronger, but before puberty, so at these young ages of 8 years old, basically they're about the same. And in fact, actually, if you look carefully, you'll see that the girls actually were a little taller in the sample mean. So in other words, the sample of girls had a higher average height than the sample of boys. That's just, a little bit of random fluctuation there. Of course, they're so close that they're virtually the same. So basically what we're saying is that it looks like this researcher is correct, that the difference in height really occurs after the point of puberty.